Today my talk will be regarding return-oriented programming and how it is possible to identify gadgets to make an exploitation. So first of all, quickly I will introduce myself. So I am Pierre-François, I come from France, and I'm currently doing a PhD in India at Kolkata. And my research topics are mostly related to operating system and low-level programming. I am speaker at c0c0n since 2019, and I already write several articles in top French magazine. So during this talk, we'll talk about what is return-oriented programming and what are the gadgets. After that, we'll show what are the existing solutions to identify gadgets to perform an exploitation. And finally, we'll see why these solutions are not so perfect. And we develop a new solution based on some machine learning model to have a more relevant one to define such gadget to make an exploitation. So first of all, we need to understand what is return-oriented programming. So first, we'll create two entities, one client and one server. Our client wants to maybe attack our server to get some information from it. So our server will be a basic web server that maybe asks your name or something else. So maybe your server has some problem of implementation for the name, for example. And you have only an array of 5 bytes, and the client is able to send 10 bytes to this array. When you do that, it's not possible to put 10 bytes in 5 bytes, or you are it's magic. So to this end, it's possible for you to send more bytes and to make the process crash. And it's definitely a big problem in security. But the attacker or the malicious client can try to go further. Maybe he can try to take control of the computer, because he can perform definitely more things. Maybe attacking another computer or something else, taking a key. So in that case, we need to use another way, because just crashing it won't be enough. So to understand how it is possible to do that kind of things, first of all, we'll see how it works in memory. In your process, you have many, many different memory space, like code memory, stack memory, and many, many others. And when you do a classic stack overflow, like your data will overflow some other data which is on your stack, and these things will be performed. So now you are the attacker, and you want to insert some code and execute it to perform the malicious action. To do that, in the past, a long time ago, it was possible to directly insert the code inside the stack. And by executing this code, it was possible to perform the malicious action. But Microsoft, Linux, Intel, all of these operating system and CPU manufacturer doesn't want that kind of behavior, definitely not. So they have implemented many, many securities, such as the data executive prevention, the NX bits, to make the stack completely not executable. So it's not possible for you to execute a code in your stack anymore. You can try, or if you want to do it, you just need to disable the security during the compilation. But for an attacker, we always want to take control of the computer. And it's not because it's not possible to insert in the stack anymore that it's not possible to do something. And for that, security researcher and attacker find a new way. For that, they use what we call the code reuse attack. Indeed, instead of inserting a code and executing it, it may be possible to use a code which is already present in memory, and by calling it at one moment which is not the good moment, it's possible to perform some bad action. This behavior is called code reuse attack because we use the code already present in memory. And the problem of that kind of attack is that they are very, very difficult to detect. Why? Because the code is there and comes from a legitimate function. It's a normal function. And if you remove it, the process won't work. So because of that, it's very difficult for a manufacturer to detect that kind of attack. And only the jump to this function is something which is not legitimate. But to control a jump is not something very easy. Because if you try to control all of the jump, it will take a very long time for you to see that. And are you ready to add some security if your computer become a kind of Game Boy? Not really. So to see how it is possible during a stack exploitation to jump until this legitimate function in that moment, we'll see more in details what is the calling convention. So you have your stack, so in a that you use all of the time, and we'll take two functions, the main function and another function that we'll call function1, which is called in the main. So we'll see how the stack evolve during all of this call. So first of all, we'll create an integer that will be put in char, excuse me, that will be put in the stack. So the value is put in the stack, and everything works. After that, we want to call function1 to perform some action. So in that case, in a normal way, it's very easy for main to know where is function1. Why? Because the instruction is just call this address. But from function1, how it is possible to come back to the main? It's not possible to directly implement in function1 the address of the main. Because if you do that, you can only call this function from the main. But most of the time, you want to call this function from many, many other functions. So to solve this issue, we just put the address where you will come back directly in the stack. And through that, when we'll execute function1, and finally function1 will be finished, we just take the address from the stack, and by taking it, we'll be able to come back in the main to perform all of the action. And it is typically how it works when you execute a program in everyday life in memory. So we see exactly the problem. The return address of a function is put inside the stack. And if you can perform some very, very malicious action, like overflowing the stack, so this address will be also overflow. Maybe you have done some tests in the past to do an overflow. And when you do that, you will see that your program jumped to some very weird values that are not very relevant. It's because it tried to jump inside a value that you have overflow. But if an attacker can choose a specific value that he wants, a value from, for example, a function like open a shell and give it to me, definitely it will be very powerful for him to take control of your computer through that. So to give a quick example, in that case, I have my cmd to a specific address, and through the buffer overflow in the main, when the main will be finished, it will be possible for my program to go inside cmd because the stack has been overflowed. So okay, now we have quickly seen how to do code reuse attack. But code reuse attack is just jumping to a function. But most of the time, when you create a program, you don't create a function, take control of my program. It's definitely not the case, except if you want to put a backdoor, but we can assume that most of the time it is not the case when you want to exploit something. So we need to find another way to do code reuse attack, because it's very powerful, but without using a complete function. And this method is called return-oriented programming. It's a very old method, so instead of using a complete function, we'll use some very small part of code that will chain together to create a new behavior that does not exist inside the process. And this new behavior will perform the malicious action. So since 20 years, Microsoft, Linux, Intel fight against return-oriented programming because it's very difficult to detect, in fact, because all of the parts of code are completely legitimate. So the first point to when we do that kind of thing is, what is a gadget? And how I am able to identify them. So a gadget, basically, is a short sequence of instruction that end with a jump. When I say jump, I don't talk about the assembly instruction jump. I talk about an instruction that will allow you to make a jump to another gadget. And that kind of instruction can be a read, indirect call, indirect jump. The purpose is not to explain exactly how we chain it together, because it can depend on your context. But for this talk, you need to understand that the last instruction is very important because it is this one that will make you the link with the other one. So each of these gadgets can be useful or not for your exploitation. Inside the binary, you have a huge quantity of gadgets. And through all of these gadgets, you need to find the relevant one to perform an exploitation. For example, if I want to open a shell, maybe a gadget to write something in memory, to take control of register, will be very, very useful for me to perform my exploitation. So now we have seen quickly how work return-oriented programming. But the final question is, okay, I know that I need to find gadgets, but how can I identify them? It's not that easy. And this question leads to two other questions. So is it really easy to find gadgets? And the answer is yes. It is very, very easy, in fact. Inside the binary, you have maybe thousands and thousands of gadgets. Like, if we take a very fast analysis with Roper, one of the tools to find gadgets, in notepad.exe you can find maybe 20,000, 30,000 gadgets. And all of them can maybe be relevant or not for an exploitation. But from our analysis, on most of the analysis, like most of these gadgets are not relevant and are just composed of garbage instruction. It is not because you have a gadget that you can use it to do an exploitation. A gadget can be just composed of instructions that are definitely not useful, maybe break, write gadget, that will just stop the program or something like that. So yes, it is very easy to find gadget. You have maybe 30,000 gadgets for one binary, and maybe more. It's not that difficult to find more gadgets. But to find the relevant one is very, very difficult. Because in that big amount of gadgets, to find the one that you need for your exploitation can take a very long time. It is to try to find this one that two kinds of tools have been developed. The syntactic tool and the symbolic tool. To quickly explain how they work, the syntactic tool will take the big list of gadgets, and just by doing some regex, like I want this instruction, I don't want this one, they are able to find some gadget, and manually, the analyst will take the gadget to perform the exploitation. The problem of this approach is it can be very difficult for an analyst to find the gadget manually. Maybe it can take hours, days, weeks, months, because sometimes the solution is not trivial. And a gadget can be very useful in some contexts and not in some others. So syntactic have a lot of limitations. That's why some researchers have created the symbolic tool. Symbolic tools are based on symbolic execution. They will take each gadget, and by doing some symbolic analysis, they will be able to know the impact of each gadget on the memory and on the register. So through that, they are able to create a complete chain of gadgets to perform an exploitation. So it's perfect. Symbolic tool seems to be perfect. But the problem is the computation time. Symbolic tools sometimes can be very, very difficult to compute. It can take hours, days, weeks, months. It depends on how many gadgets you have, the length of the gadget, and many, many other points. So we find that finally, syntactic tool can be very useful in some contexts, but when it's not trivial, it's very limited. And symbolic tools are also very useful in some contexts, but computation time can be definitely an issue. So we need to find a new way to identify the relevant gadget. And for that, we have created a model of machine learning that through a set of gadgets, maybe 20,000 gadgets, will be able to find the relevant one to do an exploitation. So for that, we'll take one objective, because when we do an exploitation with return-oriented programming, we need to have one goal. And this goal for us, it's a very easy goal, is to just take control of one register in memory. And through that, we'll try to create a model to take control of this register. There are many, many different other goals, like taking control of RCX, RDX, write in memory, read in memory, opening a shell. It really depends on you, and it can have different implications. So, okay, we want to create a machine learning model. But to create a machine learning model, we need data. And it's not something that seems to be easy because no one has created a big data set with gadgets useful or not. So we need to create that thing ourselves. So for that, we use a method based on symbolic analysis. The purpose is a symbolic tool with a long time of analysis is able, through a file, to create a chain of gadgets to perform an action, like we have seen previously. So we take a file and do a symbolic analysis on it. And we find one relevant gadget that perform an exploitation. After that, we do symbolic analysis another time, and we are able to find another things. And by removing the gadget from the initial set of gadgets, we are able, finally, to say, okay, all of the gadget that remains, once it is not possible to create any chain of gadget anymore, are definitely not useful for an exploitation. And we can repeat this process many, many times on many files to try to find many, many gadgets. And through that, we'll be able to create not so huge, because symbolic execution is costly, but an acceptable data set to perform machine learning analysis. So at the end of our data creation, we'll have approximately 40,000 gadgets, but you need to consider that 90.9% of the gadgets are not useful. And it can be more, in fact, if you increase the length of the gadget. So sometimes it can be very, very difficult to find relevant gadget. To share with you, this approach has one main problem. When we want to perform the data creation, like we have seen previously, sometimes to take control of LAX, it won't be just one gadget, but a chain of gadgets. But in that case, when we have two gadgets that will be removed from the dataset, when the algorithm will finish to find all of the relevant one, maybe G5 can be used with G2. But G2 has been removed because it was with G3. And testing all of the combination of gadgets is not possible to compute. First of all, because symbolic analysis is costly, and also because all of the combination will create an algorithm in 2 the power n, and it's absolutely not possible to compute in a huge case. So we know that when we create our chain of gadgets, we'll have some misclassification, and our data won't be perfect. But we will say that it is acceptable, and we have found a solution to not correct it completely, but improve it a bit. So, like I said previously, we'll execute our algorithm in many files, and through that we'll have our list of gadgets. So, like I said previously, sometimes, because of the behavior of one gadget misclassified, two gadgets, for example, G1 there, are the same gadget, but will have two different classifications, because one has been able to create a chain, and another one hasn't been able to create a chain. It can be a bit random. So when we find one gadget one time as useful, we'll consider that in all of the time it will be useful. So through this method, it is possible to collect a part of the misclassification. Not all of them, but a part of them. So now we have our data. So it's possible to try to train our machine learning algorithm. But first of all, we need to try to transform our data to make it, acceptable for a machine learning algorithm. So to quickly see how looks like our data, so typically we have two gadgets there. So from this one, we have the result from the gadget. Is it useful or not? To take control of the register LAX, pop LAX instruction is very useful, and the other one are not problematic, so this one is okay. We have some address, but we don't care about it. And finally, we have some instructions that are the composition of our gadget. And we can see this instruction as our feature. So to make our data suitable to be trained for a machine learning algorithm, we have applied three things. First of all, we have our gadget with all of the features. And we modify all of the instruction with some address. on some value. When I have, for example, call 0x994774.5, this specific instruction, I will transform it inside a value, a normalized value, to make it suitable for understanding. Why we have done that? Because this value, in fact, most of the time, not all of the time, but is not that much relevant. But if we don't do that kind of things, any new address, any new value will be considered for a machine learning algorithm as something new. But the difference between add ECX3 and add ECX4 is not very big, in fact. And we prefer to do that kind of things because without that, the number of instructions will completely explode, and it won't be possible for us to train any model. The second step of transformation is to normalize the size of a gadget. For that, we take a gadget, maybe 3 instructions, and add many NOP instructions before, and through that, it is possible to say that all of our gadgets are doing 20 instructions, and have no difference between a gadget of 3 instructions or 10 instructions. And the last thing, it is to encode the data, because machine learning is not magic. Most of the algorithm can't work with discrete data. So it is mandatory to transform it inside some value. And there are many ways to do it, like ordinal encoder, on autoencoder, target one, and we'll test all of them on the different algorithms. So it's okay. We have the data. So now we can try to train a model. So for that, we have tested 4 different models. First of all, the most well-known one, that are the multi-layer perceptron neural network. And we got this result. It is a log curve. The purpose of the log curve is to have a curve to go at the purpose is to have a curve that will go to the top. And multi-layer perceptron give not that bad result, but not very good, to be honest. After that, we have the k-nearest neighbor. It is a bit better, slightly better. AdaBoost is definitely better than the 2 previous ones, but the best result come from random forest and ordinal encoding. And we got this result, which is close to be perfect result. Like, we have some mistake, but it's a machine learning algorithm. It can't be perfect. So for that, we take a training set of 70% of our set of gadgets and 30% for the test. To quickly share with you, the purpose is not to go into detail, but our data is completely unbalanced, so we have tested some method to solve this problem of unbalanced data, cost-sensitive learning and smart, but we have no improvement, so we won't talk about it. So now we have our data with some useful gadgets that we are able to classify. So we can see that on approximately 8,000 gadgets with 170 useful gadgets, we are able to identify most of them and to remove 60,300 bad gadgets. So it's very easy for us to, it's very powerful, and we are able to identify most of the gadgets. So the tool is there, it's possible to use it. So we have tested it on some file from a computer, like ntdll, notepad.exe. But the problem is, when we have done that things, we got this behavior. The log curve, who was so perfect before, is always good, but not that perfect compared to previously. Why? In fact, we have 2 explanations. The first explanation is most of the files share the same gadget. And because of that, we have some biases during the training. So it's a big problem for our machine learning algorithm, because when we work in experimental environment, we haven't this biases, but when we work on Notepad, the training set can also contain some common gadget with Notepad. Another thing that can create problem is also the fact that, or like we said previously, the data that we have created is not perfect. And maybe the data set that has been created with Notepad is also not perfect. So because of that, we have also some problem, and we think it is a main explanation. So to try to solve it, we have tested different methods. And we have discovered that by using the target encoding, the result was definitely better because they gave more power to the training set during the encoding. So this method led to the creation of two main tools. First of all, like we have seen before, a gadget classification tool. So we have a set of gadgets, and we are able to classify them to create the data. And finally, the symbolic improvement tool. We take our classifier, and through this classifier, we are able to reduce the number of gadgets to analyze, so symbolic analysis can go faster. So the model can be used in both cases. So to quickly show you a demo. So we execute the script on some random file from Windows, like it must be crt.exe. And when we'll do that, we'll see that we have approximately 1,500 gadgets. It is a very small file. It is a real-time analysis. It is 30,000 gadgets, excuse me. And by doing our classification, we remove most of them, and we are able to say, to find the most relevant gadget in very few seconds. When we know that for symbolic analysis, it can take hours, it's very, very powerful one. And this one are very easy gadgets because we haven't a lot of limitation. But if you go at the top, you will find some gadgets that are not trivial to find to do an exploitation. The second demo that I want to show you is, as we have seen previously, how it is possible to improve the symbolic. So for that, we have just, it working? So for that, we have just taken the, so for that, we have just taken the symbolic analysis and our analysis by removing some gadget. And through that, it has been possible to compare both in terms of computation. So I won't wait during 10 minutes or 20 minutes to show you the symbolic analysis. So during the video, I have accelerated that, but we'll be able to see how many seconds it took for us to do the analysis with the classification and without the classification. So we see that with the classification, 97% of the gadgets have been removed, and our analysis takes approximately 100 seconds. And most of the time is, in fact, dedicated to the gadget identification, not really to the symbolic analysis. But if we perform exactly the same analysis without considering the removing of the gadget, we'll see that definitely it takes more times, approximately 240 seconds. So we have been able to approximately multiply by 2 or 3 the computation time. If we want to win more time, it's definitely possible. We just need to remove more gadgets. We'll have more false negative, but it's something that can be acceptable. So the results are the following for symbolic improvement. Most of the gadgets have been removed, so it's possible to go definitely further. To make a conclusion to this talk, like our new tool is not as good as syntactic tool in terms of speed because we need always to use the machine learning. And compared to symbolic analysis, it does not give the same quantity of information on all of the gadgets. However, it is between that, in fact. You have more information than syntactic, and you are more efficient than symbolic. And in most of the time, it will be more useful because you are in the middle, not in one of the both extremes. So thank you very much for your attention. Do you have any question? No question? Okay, thank you very much.